till we have been talking about Gaussian process regression. But if we look back at the course till now, at the probabilistic machine learning course till now, we have been primarily focusing on supervised learning. That is, we were always having access to data in form of label data set xi, ti, and based on that we are trying to learn the mapping from xi to ti or xi to yi, right? That is the problem setup we have been working on or operating on throughout this course. Again, even within supervised learning, we have been primarily focusing on regression, okay, and not classification. The reason is that in mechanics, that's what we primarily face, okay, that's what we primarily encounter, and that is why this course is designed to focus primarily on regression and primarily on supervised learning, okay. Having said that, in the homework, one classification problem has been given, which has to be solved using Gaussian process, and for that you will need variational inference, which was covered last time. I know that was little bit mathematical, so please go through it 2, 3, 4 times, otherwise you might face difficulty in following what was covered in the last lecture particularly. And after that, if you have doubt, feel free to write to me. I will be happy to have a one-on-one session and try to answer all the queries that you might have, right? So with that being said, starting today, we are going into unsupervised learning algorithm. So we will be talking about unsupervised learning algorithm starting today. I was planning to cover deep Gaussian process, but I'm going to skip that. So which means that today we will talk about mostly linear reduced order model or linear unsupervised learning model. And then in the next lecture, which is next Monday, because Thursday is Diwali, so that is a holiday. So next Monday, we'll start with generative modeling using neural networks, okay? So which means today is the kind of the starting point of generative modeling, but without using neural network, okay? And deep Gaussian process we're going to skip, because I realized if I go into deep Gaussian process, I can either cover deep Gaussian process, which will take 3 to 4 lectures, or I can cover deep generative modeling. So let's do the latter, okay? That is the idea. Okay, so with that background, let us start. So starting today, as I said, we are going to talk about unsupervised learning algorithm. So we're going to talk about unsupervised learning algorithms. So can someone remind me what is unsupervised learning and how is it different from, let's say, supervised learning? So in unsupervised learning, we talked about it at the beginning of the course. So what is unsupervised learning? Correct. The data does not have the target, or T is not available, which in other words, we work with unlabeled data, right? So in unsupervised learning, we operate with unlabeled data, right? We operate with unlabeled data. So mathematically, now my data set will look like xi I equal to 1 to n. And remember, each of these x can be a vector or a matrix. It can be many things, okay? But this is how it will look. There will be no t, there will be no c, or in one word, there will be no labels. It will be unlabeled, okay? Again, second thing, can you remind me what are the different types of, or can you think what are the different types of problem that we might encounter in unsupervised learning? So only with x, what are the type of problems we can solve? We are not going to solve all the problems, but I just want to start with that. So what are the different types of problem we can solve in unsupervised learning setup? So you have only data sets. So what are the different types of problem we can solve? Clustering, then. So clustering we'll not talk about. Then anything else? Finding a reduced representation, which is reduced order modeling. Okay, PCA, POD, those kind of things. We'll talk about that. Okay. Third is generative modeling. So you have Xi. Xi must be coming from some distribution, unknown complex kind of distribution. Can you generate artificial data, synthetic data? That's the generative modeling. Now remember, not all reduced order model can enable generative modeling, but some does. Okay. Some reduced order models enable you to generate new samples. So they are also generative models, but not all. Okay. So these are the kind of variation, right? So it includes clustering, which we will not be covering. It includes reduced order modeling. Or now reduced order modeling is a very big terminology. You can also think of physics-based reduced order model. For example, beam theory is kind of a reduced order model where you are reducing 3D into 1D. Okay. Even turbulence modeling, you can think of it as a reduced order modeling, because the actual model you are not solving or assuming, making some assumptions and trying to reduce the dimension of the problem. You can now work with coarse grid mesh. Okay. So those are physics-based reduced order model. Okay. In vibration modal analysis, that's another reduced order model where you truncate some of the modes and work with others, right? So that's another type of reduced order model. So those are physics-based reduced order model. Here, when I'm saying reduced order model, I'm talking about data-driven reduced order model. So that is the distinction I'm making. Although I'm not writing it, I am referring to data-driven reduced order model whenever I am using the term reduced order model. Okay. And third, as I said, is learning distribution or generative modeling. Okay. So these are the three types of problem that are quite common in unsupervised learning setup. Okay. Distribution learning, which is now popularly known as generative modeling. Okay. So can you, just to give examples, right? Can you give me one example of clustering? One example of clustering. You know any clustering algorithm? K-means clustering, right? So that is a very common tool that we always use. Can you think of any reduced order model? Not necessarily a reduced order model that we will be using, but any reduced order model can you think of? Data driven. Proper orthogonal decomposition or principal component analysis. So both are same actually. Okay, so let's write PCA. Okay, and do you know of any generative modeling tool? GAN, VAE. Interestingly, we wrote down three things: GAN, PCA, and K-means, out of which, as I said, generative modeling has to be probabilistic. So GAN is probabilistic, but PCA is not probabilistic. K-means is not probabilistic. And neither of these three we are going to talk about in this course. Okay. Obviously, GAN I can very well talk. It falls within the purview of this course. But because I will want to talk about diffusion and invertible, I will not talk about GAN. I will not have time rather. Okay. But if you're interested in GAN, I think I have a recorded video of GAN in a digital twin course that I took 2 years back maybe. So there is a digital twin course you will find on my website. There I took one lecture on GAN and one on VAE. Okay. So if you are interested, you can refer that. Okay. PCA we will not talk about because that's a deterministic kind of setup, but today we will talk about probabilistic PCA, which is the probabilistic variant of PCA. K-means clustering, anyways we are not talking, we will not talk about it. Okay. So with this background, let us now start with reduced order modeling. Okay. And I am starting with reduced order modeling because from there I will go into the 4 techniques we are going to talk about today, which includes factor analysis. We'll start with that. From there, we'll go into probabilistic PCA. which is an assumption or which is an simplification of factor analysis. Then from probabilistic PCA we will go into dual probabilistic PCA, which is another way of looking into PCA that you will see. And from there we will go into GP-LVM, which is dual probabilistic PCA in a nonlinear setting. So these are the 4 things we are going to talk about today. And these are very related things, so it's not like I will go very fast, and you will realize they are very closely related to one another. You cannot talk about one without discussing the other. It's kind of that setup, okay? So reduced order modeling, right? And all of these are reduced order models. Some of these are also generative models. Okay. So we are going to talk about reduced order model. So suppose we have data set D, which is xi I equal to 1 to n. Okay. So I have n data points, right? Each data point is xi and n such data points with xi, which is the ith data point, and the dimensionality of the xi point is R L. Okay. So what does it mean? That each data point is a L dimensional vector, right? Each data point is a L dimensional vector. So can you give me example of such data set where each data point is a vector? Can you think of something? So I will give you example of matrix maybe. So each data point is an image. So in that case, each data point becomes a matrix. Each data point is a time series. In that case, each data point becomes a vector, right? So you can think of it like that, okay? So suppose we have n data points where each data point is L dimensional, okay? Where L is high, okay? So this is basically a high dimensional data. So where L is relatively of higher dimension, relatively have high dimensional, okay? So now, just to give you or just to put thing into perspective, let us assume that xi or x, the variable x, is having a Gaussian distribution. We are just assuming it. It will not be Gaussian, but let's assume for now that it is Gaussian. So if it is Gaussian, how many unknown parameters are there? Okay. So just to put thing into perspective, assume assume x is Gaussian. Okay. Under this setup, what is the number of parameters we are dealing with? Can you tell me? What is the number of parameters? So if x is Gaussian, then what will be the dimension of that Gaussian? Will it be univariate, multivariate? Multivariate. And what is that multi is equal to? L. So it is a L variate Gaussian, right? Now how do you characterize a Gaussian? Mean and covariance in this case. So mean will be a L dimensional vector, which you don't know. So number of unknowns would include L as the number of unknown means, right? L plus covariance is a symmetric. Let's not go into symmetric for now. We can also go to symmetric. So for now, let's assume let's not take the symmetric condition. So then how many unknown in sigma? L square. So L plus L square. Obviously, as correctly pointed out, we can use the symmetry condition, and that will make it L into L plus 1 by 2. I just don't want to write it. So later also I'll take, so it will not matter. Because when my objective is to compare the dimension of this with the reduced dimension. If in both cases I am assuming L square and let's say they are D square, then it's okay. I should be consistent. But if you want to be precise, then it should be L plus L into L plus 1 by 2. So if you want to be precise, then in that case you are using the symmetry condition. I am not using it. So which is L into L plus 1, right? Or you can also say it is L square. If my mean is 0, even in that case it is L square, right? So the point I am trying to make here is that L is already high dimensional and the number of parameters is in square of that. So finding out this many parameters is often difficult, sometimes impossible, right? And that is the primary motivation of reduced order modeling, where you want to find out x or you want to find some reduced representation of x where the number of parameters will be much less. Okay. So the objective in reduced order modeling is to find a reduced representation of x. Okay. Clear? The objective is clear? Now, there is a quotation, not by me, by Neil Lawrence, who is one of the topmost person in Gaussian process. I think deep Gaussian process is also developed by him. So what he stated was in one of the talk actually, that any real world data, any real world high dimensional data will always have a reduced representation. If it does not have it, that means you are working with noise, because white noise is something which does not have a reduced representation. So if it is not noise, then it will always have some reduced representation. So that is one of the statement by Neil Lawrence, which I kind of attest to, and I kind of believe in that, because anything you look into, you will always find, if it is a real data, there will always be some data generating process which is generating it from some low dimensional space. To give you one example, suppose those who have studied about state of stress, right? So stress is stress is defined at a point, and it is having 6 components in 3D, right? Using symmetry. But then if you rotate, it changes, right? So what is the reduced representation of that stress? This is only for those who have done the APL 104 course or solid mechanics course any. Okay. So what is the reduced? Can you think of any reduced representation of stress? That is 1, but that is still 3. Can you reduce it further? And the principal stress is not enough, because then you have to rotate it and then find it out. So you will also need the angles and all those things, by the way. But even if I take principal stress, that is 3. Stress invariance is also 3. Anything else? More circle. You will need 2 parameters, the center and the radius. So with 2 parameters you can represent that. So that is, so like for circle, you might have many data on circle, but the reduced representation is the equation. If you can find the equation of that, is like, that will take the minimum memory. Okay, you will not always get like this. Okay, what you will get is probably some reduced order vectors. You will never get what I am giving. I am giving very idealistic scenarios. You will not always get equations. You will not always get such reduced representation, but you can potentially get a reduced vector from where the data is being generated. And this fact that you can get a reduced vector from where the data is generated is the fundamental building block of any generative modeling. In any generative modeling, you assume that there is a Gaussian distribution or some distribution, which if you transform will give you the high dimensional distribution. So that all you need to learn is the mapping from a Gaussian to the target distribution. And you will keep generating samples from the Gaussian, pass it through that mapping and get samples of X. Okay, that is the basis of any generative model you can think of. GAN, you assume there is Z which is generating, and then you do something with that, right? There are 2 networks basically, and then you optimize them together to find out the generating process, the generator x, z to x. The other one is discriminator, which you don't need during the generating process. VAE, again same thing. You have data, you reduce it to z and then go back. Any model you can think of is of that sort. And this is based on that assumption that, not assumption, this observation rather I will say, that any high dimensional data is generated from a reduced space. And at that reduced space, things are independent. Clear? So, we assume that X is generated from low dimensional, X is generated from low dimensional Z, which belongs to RD. Okay? Where D has to be much less than L. Right? We assume that X, which is my high dimensional data, is generated from some low dimensional data Z, and this low means it is significantly lower than the actual data dimension. Okay? With this assumption, or with this consideration or observation, whatever you call it, what you can do is you can write X1 data as some function of Zi, okay, where your Zi comes from a Gaussian distribution, okay, with mean, let's say 0, and covariance, often we work with 1, we'll come to 1 later, but maybe let us take 1 only, or we can take 1 for now, okay. Most of it, or I, not 1, I, because it may not be univariate, so I, right? This equation is clear. The message that equation is trying to give is clear, that you have Z, which is coming from a known, in this case Gaussian, in most cases Gaussian, but low dimensional Gaussian distribution, and if you can generate sample from that Z, pass that Z through a function, deterministic function, or maybe probabilistic in some case, which will give you now X, and this X are supposed to be samples of X, the data set you have. Is the setup clear? Any question on the setup? So if there is no question on the setup, all generative models are based on this, and today we are going to talk about factor analysis. We'll start with factor analysis. So factor analysis is also based on this, but factor analysis is a linear model. In factor analysis, we'll assume F to be linear. Okay?
This is need to be same. Like xi equal to f of zi. Those both need to be I.
Because that's a sample. So Zi is a sample from Z, Xi is a sample from X. No, not index. It's not a variable. It's a sample. So in that case, okay. It's not X1, I mean, not the X1 variable. It is the ith sample. So in that sense. Okay. Clear? Okay. So then with this background, we can now come to factor analysis. Factor analysis. Okay. So in factor analysis, first come the modeling assumption. The modeling assumption is that your Xi is equal to W times Zi plus epsilon, where epsilon is coming from a Gaussian with 0, psi. Clear? This is the modeling assumption that F in factor analysis takes this form. That F takes this form, and if F takes this form, then you call it factor analysis. Clear? And remember that psi you are going to assume it to be diagonal matrix. So this is diagonal matrix. You can also work with full matrix, but it is pointless. I mean, most of the time you don't, right? because anyways W will cater for any dependencies in that sense. Okay. So now this is my model. Clear? What are the unknowns in this model? W, Zi, and psi. Now Zi we are already assuming it to be standard normal, right? So okay, first let us write down the likelihood. So the likelihood is, and likelihood is, this is of the ith data point, remember. What I am writing is for the ith data point only. So xi given Zi, comma W, comma psi. Okay, what will be this distribution equal to? We have done it again and again since linear regression. What will be the likelihood? Gaussian of xi. What is the mean? No, it's condition on Zi. 0 will come later. WZi. What you are saying is correct, but that will come in the next step. Marginal it will come. So W, Zi, and what is the variance? Psi. Okay. Clear? Now you cannot work with this. W is not observed, Zi is random, so you cannot work with this. So what you will do is you will assign a prior on weights. Okay, you will assign a prior on weights, or you can assign a prior on Z also, depends. In this case I have assumed Z to be Gaussian, so we will work with Z, we will not assign prior on weights, we will try to estimate the weights. So there are two ways, think about it. One, you assume Zi to be 0 mean Gaussian, okay, and then you find out the marginal likelihood, and from the marginal likelihood you try to estimate W. That is one way of doing things. The other way is you assign a prior on W. Now in that case Zi will not be a standard Gaussian, it will be something else. Okay. So we assign a prior on W, integrate out W, and then find out the reduced coordinate Z, and psi obviously has to be found out. So there are two ways of doing things. So we'll start with in factor analysis, and in factor analysis you integrate out Z, not W. Okay. So in factor analysis, you have probability of Zi is a Gaussian over Zi given 0, comma I. Okay. Now here is a now this equation I wrote might create some confusion. So let me clarify that. Zi is a sample, right? And I am saying the sample is following a distribution. Why I can do that? Because Zi is not observed. It's a latent variable. Because Zi or Z is a latent variable, you have not observed it. So every time you draw, your samples can change. So each sample is also a Gaussian in that sense. But when we do it in the linear regression setting, X is observed. So in that case, you don't assume X to be some, you don't do that. Here you do that because Zi is also unknown. And it's a assumption we are taking, right? Then it's a sample you are drawing, so in that sense. Okay. So therefore, once you have done this, so tell me then what is the marginal likelihood then? Because it's the same GP setting that we are working with. Marginal likelihood is probability of xi. I am still working with single data point given Zi. This will be equal to what? You will do the product of 2 and then integrate out. Sorry, not xi Zi, xi W. Sorry. W, comma psi. I am not writing psi. Okay. W. So what will you do? You will do a product of 2 and then integrate out Z. Correct? So this is equal to integration of Gaussian xi given W Zi, comma psi, Gaussian zi given 0 comma I tzI, right? And tell me what will be it equal to? This we have encountered now multiple times. So what is probability of xi given w? Probability of xi given w then is equal to what? Normal xi given 0 comma w transpose plus psi, right? Because I is there, so that I may or may not get w transpose plus psi. Okay. So this comes out to be my marginal likelihood. Maximize it to find out w. Okay. Maximize to find w. Okay. And once w is known, you can generate new samples of z. Obviously, w and psi. I'm not writing psi, but maybe I should write w and psi. Okay. So once you know w and psi, what you can do is you can generate new z from standard Gaussian, pass it through the model, and you will get new x. It is also a generative model, or rather, it is a generative model. But why is it a reduced order model? So what are the number of parameters now with this setup? Can you tell me? Number of parameters. What are the number of parameters? W is unknown. What is the size of W? LD, right? And then psi. What is the size of psi? L. So LD plus L. So L into D plus 1, right? Which is much less than L into L plus 1. Because D is much less than L. So that's why it's also a reduced order model. So number of parameters, if I only take W, then it is LD. Okay. And which is much less than L square or whatever. So LD, and plus if I take psi, it will be plus 1 L. So L into D plus 1, which is much lower dimensional than the original data that we were working with, right? So that's why it's a reduced order model. It's a generative model because you can now generate new x. It's a reduced order model because the number of parameter space has reduced. Clear? So it is both. So this is all for factor analysis. Okay. So how to solve it? You know how to solve it. You might need a numerical optimization, but same thing as GP. You will take the negative of log and then write it down in that form, the same form. Minimize that because I've taken negative. And that from there you will find out W and psi. Same thing as before. Okay. So nothing changes. The only thing that changes is that this is an unsupervised learning, and this is the generative model, and this is a reduced order model also. Okay. Any question? Clear? So now if it is clear, then let us go to probabilistic PCA. And probabilistic PCA is a special case of factor analysis. Okay. So let us go to probabilistic PCA, which I will write as PPCA or PPCA. Okay. So in PPCA is a special case of factor analysis where your psi is equal to beta inverse I. That's all. So right now I said psi is a diagonal matrix. So diagonals could be different. Correct? So you had L parameters. In PPCA, you just make one change. Psi is equal to beta inverse I or sigma square I. And if you do that, that is our PPCA model. Okay. So in factor analysis, if we consider psi is equal to sigma square I, which is equal to beta inverse I, then we call it the probabilistic PCA model. Then we call it the probabilistic PCA model. Okay, clear? What is the change? Only one change. Psi, instead of being diagonal, it is still diagonal, but the diagonals are same, which is sigma square or beta inverse. Both are same, right? Clear? So now in this case, what is my marginal likelihood? Can you tell me? So therefore, okay, there is one step I missed, so that's okay, I guess. So probability of xi given w will be equal to what? What will be it equal to? Your psi will get replaced with sigma square I or beta inverse I. That's all. Gaussian of xi given 0, comma w transpose plus beta inverse I. Okay, clear? Now this is for one data point, by the way, don't forget it. If I have n data point, then what will happen? Assuming n data, I will get probability of x given w is the product of, because the data are IIDs, that's our assumption. So because they are IID, just do a product over n Gaussian xi given 0, comma w transpose plus beta inverse I. Right? IID, simple thing. Okay. And then you will try to maximize it to find out. Okay, this is a name, by the way. This is known as my, you can call it CN, okay, or C. I mean, that's the name I am giving because I will need it. Okay. Now, this has a closed form solution. Okay, you have a closed form solution for this, which is equal to, any idea what will the closed form solution look like? It has a closed form solution. Any idea? The derivation is a little bit tricky, but I will give you a clue. It is called PCA. So in PCA, how do you get the solution? By doing eigenvalue decomposition of C. So in this case also, you will do the same thing. You will do eigenvalue decomposition of C, and the solution will be based on that. The solution will be based on eigenvalue decomposition of C. So what you will do is you will write the covariance matrix in terms of X. Okay, you will write the covariance matrix in terms of your data, and then do eigenvalue decomposition of that. So let us do it here. Okay. So Cn is what? Covariance of let's say x comma x dash, something like that, right? Cn is the covariance of x comma x dash, right? So what you can do is, okay, let me give you the solution first. The final result is W is equal to ud lambda d minus beta inverse I to the power half. So this is the final solution you are going to get. Okay, so I am giving you the answer first, because I am not going to solve it, I am going to give you intuition of this. Okay. So now you have Cn, which is the covariance of your, Cn is covariance of your data, and you can find out Cn by, because you have measured x is measured, so from there you can calculate Cn directly. So now we'll arrive at this result in a short while. So I'll put it in a box. So can I write Cn as U lambda U transpose? Can I write it like that? I can, right? That is the eigenvalue decomposition I've doing. So this is my eigenvector, and this is my eigenvalue, eigenvector, and this is my eigenvalue matrix, right? The diagonal matrix of lambdas. Correct? I can do that. Clear? Any matrix, if you do eigenvalue decomposition, this is how you can write that matrix. Now, what I'm going to do is I'm going to write it as UD lambda D UD transpose. So D is the first D dimension, the highest eigenvalues I am taking. Why highest? Because they have the most amount of information, or in other words, they capture the maximum energy of the data. Plus U D tilde means n minus D. So if there are n dimension, so you have taken the first highest D in separated out, whatever is remaining, that is D tilde. Lambda D tilde U D tilde transpose. So it is basically decomposing the first you are decomposing the covariance, which is based on your x, into the eigenvalue, and then you are separating it out so that you have the highest eigenvalues in one matrix and the lowest one in other. Clear? So I'll repeat here. What I've done is that Cn is my covariance of the data. I have measured data. From there I can calculate Cn. Correct? And if I can calculate Cn, I have that matrix. I will do eigenvalue decomposition of that. That will give me the eigenvectors and eigenvalue. Now I am here writing that as the leading eigenvalues separately and the preceding or the remaining ones separately. That's all I am doing. Right? So now you have data, right? Is your data, can you collect data that is not noisy? You cannot. Your data will always have noise. The idea here is that the highest eigenvalues, those are the actual information that your data is having. Whereas the lower ones, D tilde, are the ones that are noise in your data. So what you do is you remove the second part, because that is like the noise in your data. So you remove those. Okay, so let me write it down here. So UD lambda D, this corresponds to information in data, and UD tilde lambda D tilde correspond to noise. Okay. So if that correspond to noise, what should we do? We should ignore those. Right? So this is, therefore we ignored it. Right? Clear? Why we are ignoring it? Clear? So then what do I have? I have UD lambda D UD transpose. This is supposed to be equal to what? This is supposed to be equal to WW transpose plus beta inverse I. That is what I got from mathematics, right? This is supposed to be equal to WW transpose plus beta inverse I, right? So which implies WW transpose is equal to UD lambda D UD transpose plus, sorry, minus I'm writing an equation, you tell me what I have done here, okay? UD beta inverse I UD transpose. What have I done here? Can you tell me? The second term, so instead of beta minus beta inverse I have written that, right? So what property am I using? Orthonormality. Because the eigen, so I'm not using just any eigenvector, I'm using the orthonormal eigenvectors. And if I'm using the orthonormal eigenvectors, U transpose will give me 1. So if that is supposed to give me 1, I can always write in this form. Beta inverse is a scalar, does not matter. I is the identity matrix, does not matter. So I'm using the orthonormality property. Correct? So then what do I have? This implies W transpose is equal to UD lambda D minus beta inverse I UD transpose, right? So it is like a square, W square is equal to something. So W will be equal to square root of that. So if you take square root, the transpose will vanish. The middle term will be to the power half. So therefore, W is equal to UD lambda D minus beta inverse I to the power half. Okay, half because diagonal. That is the diagonal matrix. Lambda D is diagonal, beta inverse I is diagonal, so that's why. Now this kind of form you can get only for probabilistic PCA. You will not get it for factor analysis. Because there beta inverse I will be something different, and that might create issue. Okay. But for probabilistic PCA, you get it, and because you get it by eigenvalue decomposition of the covariance matrix, that's why it's called PCA. Otherwise, the motivation is kind of different right here. But it's called probabilistic PCA because ultimately the form looks the same. Ultimately, you are ignoring some of the higher order, the low eigenvalues, as you do in PCA. And all those tricks are the same, so that's why you call it PCA. Clear? So now, let me give you a graphical illustration of what is happening here. So we are done with probabilistic PCA, just a graphical illustration of what is happening here, okay? And then we'll move into dual probabilistic PCA. So, suppose this is my Z, and this is probability of Z, the PDF. So let's say my Z looks something like this, Gaussian, right? Although what I've drawn is probably not Gaussian, but let's take it to be Gaussian. Okay. So this is my Z, which is a low dimensional. In this case, one dimensional. Clear? I also have x1 and x2, which is the high dimensional. So for this case, high means 2, low means 1. In reality, high will mean millions or thousands, low will mean tens or hundreds. Okay. And let's say this is my function. So think what is happening. What you are doing? You are drawing a sample from Z. You are drawing a sample from Z. So let's say that point is here. Let's call it Z1. Then what are you doing? You are transforming it into X space, W times Z plus epsilon N. So this gets transformed somewhere here. So you get a point here which is what? W times Z1, right? But now you also have that epsilon, which is the noise term. So what will you get? You will get a Gaussian centered around this point. So it's a Gaussian centered around that mean value. This is what you are getting, right? Because it is WZI plus epsilon. Epsilon is Gaussian, so that's why. And it's beta inverse, so same in all directions. It will be circular, not elliptical, because it's in like beta inverse I. There is no dependence. Clear? So remember this formula. WZI plus epsilon. But in probabilistic PCA, epsilon is beta inverse I. So now Zi is my this one. The left one is my Zi. So Z1 is this one. So you select Z1, you draw a sample from that. Then you transform it to X. What is the mean of that? W times Z1. So that's what I have shown here at the middle. W times Z1. And then what is the variance, or ultimately what is the distribution of Xi? It's a Gaussian. So that's a Gaussian centered around that point. So that's what I have shown. Clear? Suppose I have another point. let's use this one. And let's say this is my point, this is known called Z2. So I have drawn another sample from Gaussian. That sample, perhaps, I don't know, W is such that it goes here. So then this point will become my W times Z2. W will not change, you have learned it. And then there will be a Gaussian around that. Right? So this will give you, so each point you are getting a Gaussian. Okay. What is probability of X? You have to find the probability of X. What will you do? You will marginalize out Z. So probability of X will be some Gaussian which will be now elliptic or maybe elliptic, because now, so it is basically average of all these Gaussians you will get. And this will be obviously, the mean will be on the line. My mean is a little bit off, but it will be on. So this is your probability of X. So this green is your probability of X. Clear? So each point you are getting with some distribution, but if you average it out, you get, because that's the sum law. Averaging out is sum law, integration of fx, right? So if you do the sum law, you will get probability of X, marginalize out Z, and then you get this thing. Clear? So this is what is happening through the mathematics. Yeah. The line, I draw it that represents the mean, maybe. Okay, in some sense, because all the means you find out will stay on that line. So in that sense, is the variation of mean. Okay. Or it represents all the data points you have measured. That's also is possible. Okay. Okay. Clear? Okay. In doubt?
Every sample is considered IID. Every sample is considered IID.
Zi is IID.
Not the X sample.
X, obviously IID, because that's how you use product of that, right? Yes. So the samples you have are IID. Clear? Okay. So now let us move to the third part, which is the dual probabilistic PCA. Dual probabilistic PCA. Okay. So now, till now, what we were doing was that we were assuming Z to be a Gaussian. So probability of Z was like a prior kind of thing we are assigning, and we were finding out probability of X given W. But in reality, your both Z and W both are unknown. Correct? So probably a dual probabilistic PCA is a complementary of probabilistic PCA, where now what you will do is you will assume or you will assign prior on the weights. So previously you were assigning prior on the Z and finding out W. So now you will assign prior on the weights and find out Z. So because you are doing the exact opposite, you call it dual. So it's not a dual, means you are not integrating out both. It means it's the dual form of the other. So it's a complementary form of the other. That's what it means. Okay. So here, first of all, the first expression remains same. Probability of xi given zi, comma w, comma beta should also be there. I'm not writing it. This is equal to Gaussian xi wzi, comma beta inverse I. Okay. The likelihood remains the same. No change in the likelihood. So that means the model remains the same. So the model is wzi plus epsilon. That model remains the same. Correct? So what we do here, what is the change? The change is in the prior. We assign prior on weight. So prior is now on weight. Now what is W? What is W? Matrix. So we are trying to assign a prior on a matrix. So one way is to assign matrix normal distribution. We will not do that. What we will do is that we will assign row wise. So that means each row will be assumed to be independent. So it will become product of the priors of the row. So that means it is L comma D, right? So I is equal to 1 to L probability of Wi. Now remember, Wi means the ith row. Wi means not the ith element, is the ith row. Clear? And this is equal to phi I equal to 1 to L a Gaussian over Wi given 0 comma I. Clear? This is little bit different. So take a note of this or understand it very carefully. W is a matrix. So you are now trying to assign a matrix, a prior on matrix. So it has to be some matrix distribution. So one matrix distribution is matrix normal, for example. And in matrix normal you have two kind of covariances, right? So, but we will not do that. What we are doing is that we are assuming each row to be independent. So then that means it will now become product of different vectors, L vectors. And then each of those vectors is now a multivariate Gaussian. Clear what we have done? Okay. So now, previously what were we doing? We were finding out probability of xi given W and then doing a product over all the I. Here we cannot do that because there xi and zi were both n and we are factorizing over xi and zi. If it was dzi, we could do that. Here that will not work because here W factorizes over L, whereas your data point factorizes over n. So that means the integration has to be done together. So this is little bit more involved. You will need a matrix algebra concept to do this. Okay. But anyways, I will just give you the answer, and the intuition. So marginal likelihood will be probability of x given z, okay, which is equal to integration of first product I equal to 1 to n Gaussian xi given wzi comma beta inverse I. That is my likelihood. And then the prior product j equal to 1 to L Gaussian wj again row, jth row, not the jth element, comma 0 comma I, and then dw. This is what I will get. Clear? This portion is clear. Any doubt? Check it carefully. Okay. So the integration is now over the whole thing because each term has W. Although the prior has been composed in terms of W, Zi has not been, at least not in this formulation. Correct? So you'll end up with something like this. Now, without solving this integration, just from intuition, can you tell me what are you expecting here? Let us go step by step. Look at the prior. Prior is what? Prior is what? Product over multiple Gaussian. What is product of Gaussian? Gaussian, we know that. So prior is a Gaussian. Okay. What is the dimension and all those things? Let's keep it aside, but prior is a Gaussian. likelihood is a product over Gaussian. So it is going to be a Gaussian. So now you have integration of Gaussian. So convolution of Gaussian. So what is convolution of Gaussian? So what will you get? You are going to get Gaussian, but not a straightforward Gaussian, right? So what you will get is, at least the intuition is clear, that you will get Gaussian, and I am giving this space because I will write a product there, over Gaussian over what? Not xi, because I here denotes the data point. Here you cannot get over data point because you are integrating total. But the trick here is to observe W. What is W? Rho, right? And you have W times X. So what is W getting multiplied with? Wi is getting multiplied with what? The ith column of X. Because I is the ith row of W, which is getting multiplied with the ith column of X. So I'll write it later. Let me just first write it down. So think about it. W is something like W11, W12, W13. Let's take 3. W21, W22, W23. And I will delete this, by the way. So it's better if you take note. Right? Okay. Now, this is a very bad example. I took 3 by 3. It should be 3 cross 2. So let's delete the third one. Okay. Otherwise, it's a bad example. Okay. So L is your 3, D is your 2. This is getting multiplied with what? Z. Right? Z1, Z2. What will you get? X1, X2, X3. Right? Now you tell me, what is this Z1 and Z2? Z is obviously latent variable, that I know, but what is Z1 and what is Z2? What are these representing? And what is X1, what is X2, what is X3? What are these representing? What? Vector. Element, but what does it mean? Not sample, because this is one sample. Z1 and Z2 is one sample. So this is not sample. That's exactly what I want to show or discuss, that Z here is not sample. Each sample of Z is two-dimensional. This is like one sample of Z, it has two elements. So what is Z1 and Z2? The dimension or the features, the input features or the features, hidden features, right? Similarly, X1, X2, X3 are the features. So now you see, so these are the features, okay? Feature of the maybe ith data point, I don't know, but feature. So here the Gaussian you will get is over features because you have taken W. So you will get it over features. So you will get X colon comma, what was it? Maybe let me write K. Given, you will get it over the featured because W you have assigned row wise. So that's why you will get over each features. Given, what is your mean? Mean is 0. Tell me what is the covariance? It is W times Z, right? So we will get it Z transpose, and this is all the Z, by the way. So you will get Z transpose plus beta inverse I. I will repeat once more why you are getting over features. So remember, the weights are decomposed row wise. So what is the first row of weights representing? It will get multiplied with all the z's, but give you x1. So first row is giving you the first feature. Take the second row, that is getting multiplied with all the z, but giving you x2, the second feature. Take the third one, w31, w32, that is getting multiplied with z1 and z2 both, but giving you x3, the third feature. So that means the row is representing feature. So that is the intuition. Okay, you can obviously derive it. It will be a 3-page kind of derivation, but the intuition is very simple, that each row of the weight is associated with the features in the original space. So this will be equal to then product k equal to 1 to L. Is it clear? Okay. So let me repeat once more. So the prior is assigned in such a way that I am assigning prior over one row at a time. One row of the weights. So now if you take one row, let's take the first row of the weight. You will realize that when you multiply with z, the first row only give you the first element of x. Not the first data point, first element, the first feature. So because you are decomposing weights in that manner, what you will get is, you will get one feature corresponding to each w. W means w row. And that is why you can write it in that form, where x colon comma k is the kth feature of x. This is the kth feature vector of x. And why am I writing like this? So that also you will have to understand, because x, how do I write x? X I write as x1, x2, x3. So the x matrix, each column in that matrix represent one feature and different data points, because you will have n data points. So each column is representing the n data points for the ith feature. That's why when I'm writing x colon comma k, that means I'm taking the kth column from this x matrix at the below, and that is only what you are seeing there, x1, x2, x3. Because remember, it is also over all the data points. So over all the data points, that is denoted by colon. So it is decomposed feature wise, but over all the data points. Previously it was decomposed data point wise, but over all the features. That is the change. Clear? Think about it carefully. I have 10 minutes time and I have one line to say. So you can think about it, because from here to GP-LVM is just one line. So this is dual probabilistic PCA. From here I will just say one thing and it will become GP-LVM. Okay, so therefore this is very important you understand this thing. Okay. And if you remove that, okay, one more question let me ask. What will happen if I remove that product? What will you get? How will the covariance look like if I try to write it over all the x? Any idea? If I write it over all the x, how will it look? It will become trace of that. It will become trace of z transpose plus beta inverse I. Okay, you can do the derivation, but that is not needed. This is the form I need. Okay, but if you find out, if you remove that product, it will become trace of that, because they will get exponential, right? They will get added up in that sense. So let me repeat once more. In this previously, x and z both were getting stronger. Previously, x and z both were getting decomposed over data points. So it was very simple for us to write xi given w, because I can integrate out zi independently, right? But now in dual, our prior is on w, and w does not depend on number of training data. It depends on number of features, input and output features. So as a result, the integration becomes little tricky because now it is over all the W's together. But it is quite easy to observe that it comes out to be convolution over Gaussian, right? Since it is convolution over Gaussian, therefore you are going to get Gaussian, and then because we are taking one row at a time, weights, that will give me one feature, so that it will be product over features. Clear? So now, as I said, I will need one more line, right? So can you tell me what is Z transpose plus beta inverse I? Does it rings a bell, that expression? You can ignore beta inverse I for now, but what is Z transpose? Does that ring a bell? What is Z transpose? Okay, let me put it this way. I have data X, okay? I have normalized X or scaled X so that the mean is 0. Okay, so I have data of X with mean 0, I know that. Then what will X transpose give me? No, it will give matrix. But what does that matrix mean? It is outer product, it will give matrix, I know that. But what will that matrix mean? It has a meaning. Covariance matrix. It is a linear covariance matrix, right? This Z transpose plus beta inverse I is nothing but my linear covariance. If you take, that's what you get, right? So notice that Z transpose plus beta inverse I is the linear covariance, and you know that correlation and covariance, these are all linear measure, right? Linear covariance. And this is giving, why is it giving linear covariance? Any idea? Where is this linearity coming from? The assumed model is linear. W times Zi, that's a linear model, right? So if I assume a nonlinear model, what will I get here? A nonlinear covariance, okay? Extending it, we can write probability of X given W is equal to product K is equal to X given Z, right? X given Z, yeah, sorry, not W, Z. K equal to 1 to L Gaussian X colon comma K given 0, you add a covariance kernel between Z and Z dash plus beta inverse I, right? What is this reminding you of? This is the marginal likelihood that you get in Gaussian process. So then with this setup it becomes a reduced order model which based on Gaussian process. So that's so, and that is why it is called GP-LVM, Gaussian process latent variable model. Why latent variable? Because Z is not observed. Okay. So this is known as GP-LVM because this part is corresponding to GP kernel. GP kernel. And remember, you will now have to optimize it or maximize it to find out what? Z. You have to find out beta, and you also have to find out the hyperparameters, sigma square and L, because whatever kernel you select, that will have its own hyperparameters. Clear? So this is the GP-LVM, which is a nonlinear reduced order model. Reduced order model. Is it clear why is it nonlinear? Why is it nonlinear? What is making it nonlinear? The kernel K. How will you make it linear? use a linear kernel, ZZ transpose. And if you use a linear kernel, that is as good as using a dual probabilistic PCA. Okay. Non-linear kernel, you call it GP-LVM. Okay. So I have 2-3 minutes. Let me make one announcement and give you one high level idea. So I said I will not cover deep GP because I will not have time. I will directly go to generative modeling, neural network and all those things from next lecture, okay, which is next Monday. Deep GP is nothing but multiple GP-LVM stacked on one another. Okay, GP-LVM is that. You stack multiple of this GP-LVM and that's how deep GP was proposed. It was proposed by Lawrence only. So he first proposed GP-LVM and then proposed deep GP. Okay, it is multiple GP-LVM stacked on one another. The training becomes difficult, and deep GP is a nonlinear model because when you pass one GP through another, you get non-Gaussian process. Okay, that was the one small thing I want to tell about deep GP because we are not going to discuss it. I thought it is better to mention that so that if you want to learn deep GP, you have all the ingredients now. You know GP-LVM. Obviously, it's kind of superficial until and unless you do homework on GP-LVM or practical on GP-LVM. It remains superficial. You have to do it yourself to understand. But once you understand it, deep GP is basically straightforward extension where you stack multiple GP-LVM on top of one another. And it's called deep because multiple, more than one. Okay. So that is it for today. So on Wednesday, I will not take any practical. Okay. If you want, I will be available. So you can come to my office and we can have a discussion. But I'm expecting many of you will not be here because Thursday is Diwali. But if you want to discuss something, directly come to my office or write an email. If there is 4 or 5, I have anyways booked a room, then we can go to it. But if I don't receive enough email with doubts and all those things, we will not have any practical on this Wednesday. Okay. And the remaining lectures will be on neural networks. In particular, it will be on invertible neural network and diffusion model. Okay. So that is all. Any question? By the way, the syllabus for the major is until this point. I will not give any question in the major from the neural network part because I cannot. Those are like you have to write codes. So in major, it will be this time, you know, right, that it will be written proper kind of exam on the date assigned by the institute. But the syllabus of the major is from starting to this point. I will not give question from the neural network part, which is I will not ask any question from invertible or generative, but expect question from that in homework, but not in the major. Okay. Any questions? Okay, then thank you.